We're live. Go ahead, Ollie.
All right, so welcome guys. Let's see here. I'm just gonna. So can all of you see me now, or see my screen?
Yep.
Cool. So I'll just paste the URL here if you want to follow along on your site. So let's see. Right. Okay. All right. So most of you probably know a bit about Frida, but I'm just going to run quickly through like how it started or why it started, and it's basically I've been doing a lot of reverse engineering, and every time or very often there's this common thing. Okay, I would really like to have a tool for this because I need to like look at this particular API or look at what would happen if I do it like this, and it's quite a lot of work to build a tool from scratch, and existing tools aren't really suitable for this, and I would like to have a really short feedback loop when doing this, because your understanding of the problem tends to evolve as you go along, and then you need to adapt the tool, and if you have a long process, then yeah, you're just going to waste a lot of time, and in the end it might be better to just do things by hand and go through the painstaking debugging. And I would also like to have one toolkit, so that whichever platform I'm currently on, there's just one toolkit I need to learn once, and of course there's platform-specific bits involved, but at least I don't need to relearn the basics every time. And this kind of started because I had back in 2004, 2005, I was doing a lot of reverse engineering of product calls. At the time, I think it was ActiveSync for synchronizing contacts on the phone, because I had just gotten a Windows mobile phone because I was curious about that. And there was also some Windows Live Messenger protocol reverse engineering at the time because I was using Linux, and I wanted to have a good feature set, and like I wanted to build the first client that could do webcam chat, basically, and yeah, that led me down a rabbit hole of reverse engineering video codec, but that's that's a long story. Anyway, I ended up building a tool that was called OSPI that looks like this. It's kind of like Wireshark, but it works at the API level, and you can then look at encrypted communication and yeah, pretty much anything. But the thing is, this was written in C#, and then with I injected code into the target process to instrument it, and that was written in C++ or C, and it's a lot of you had to write code there and deploy it, and it's a long cycle. The feedback loop was really horrible. So, but it helped for the problems I had back then. But yeah, it was a slow thing to evolve. But here you can see, basically, I'm looking at a particular function call and the backtrace for it, and you can go to you can visit the return addresses in IDA. There was an integration with that, and here you see how it dealt with encrypted communication. It was intercepting things there. And it also had like a timeline view where you could look at how different protocols worked in tandem. So here there would be like a proprietary protocol happening on one port first, and then it would switch to a sidebar with another protocol. And yeah, so I had like a timeline view for that. So that's just a bit of like why I ended up just like going down this side path of building a dynamic instrumentation toolkit, which is Frida, to be able to build such tools very quickly, basically. And so yeah, that's what it is. It's an dynamic instrumentation toolkit, and it's scriptable. So it works by injecting pieces of JavaScript into remote processes, and it works on several platforms. and it's open source. And yeah, you know these things. I'm just running through it. So basically, yeah, it's quite obvious why you would need it. But the bottom line is that we want to be able to enable rapid development of new tools for the task at hand, because the task at hand changes and it evolves as we work on it as well. So so being able to just incrementally build that tool by doing changes live is basically where I would like to be with this. So yeah, maybe we can just dive straight in and just demo some APIs, because this is a toolkit. So if you're building a tool, you'll be using the API, but there are also some existing tools built with using the API that we will also talk about. But for now, let's just dive straight in. So here, let's just build a target application where we have a lot of control, and that's going to make it a bit easier to understand what's going on. So I'm just copying this code here, and so this is our hello. Yeah, maybe this is a bit small. So can you all see this?
Yes.
Cool. So yeah, we're just going to compile that and run it. And here we go. So this program here that we have is just an eternal loop that's calling a function with an argument that increments with every iteration of the loop and sleeps 1 second between each invocation to this function. So yeah, we need to take note of the address of f. So we got that here. So now let's move along, and we're going to look at how we can hook this function and get notified when it's called, and do whatever we want. So we're going to just create a hook.js file. But before you do this, you need to npm install Frida and generator async, this line here, and then we're just gonna copy this code here into. I'll actually. Hook.js. So I'm going to explain a bit about what we have here. So we're using, Frida has bindings for several languages and runtimes, and the one we're going to use here is the Node.js one. So we have installed the Frida package, and we also installed the generator async package to help us with the to avoid callback spaghetti, basically. So here we're just, because the Frida API is asynchronous and it's returning promises, and this just simplifies things a bit, so we can yield instead of having a chain of callbacks. So yeah, we start by attaching to the process named hello. We could also give a PID here, and we create a script. So we take this function here of JavaScript, and we call toString to turn it into a string. And then we just add a preamble, and well, we just add a wrapper around it, so we can and call it. See, that's our script. And then we hook up, before we load the script, we listen for messages, so we're ready. So in case it sends a message immediately when it's executing, because when you call load here, it's actually going to execute this script inside the remote process. So what this script does is that well, we have our we do interceptor attach to get callbacks or intercept function calls to this function, and we know here that this function is at this address. So we're just going to substitute that, and every time this function is called, we're going to get this callback on enter here. You can also define an on leave if you're interested in the return value, for example. So I'm just going to run this hook.js. As you can see, what we do when it's called, we send the first argument sending a message to the Node.js side, which is going to console log that message when it gets it here. Yeah, right. Actually, we can save some time and just copy this. Here we go. Now you should see that it's hooking the function calls that are happening. So yeah, any questions?
Just want to comment. It's so easy.
Cool. So let's move along and see if we can do something more exciting than this. Yeah, we could also show how we could do this from Python, but yeah, why not? Let's just do it. We can write a hook.py, and it's basically the same thing, except it's a blocking API here, so there's no promises involved. A bit easier to use, but less flexible. Yeah, exactly the same thing, pretty much, except here we use an inline multi-line string instead of having a JavaScript function that we toString, so it's a bit harder. But anyway, in most cases, you would end up it's easier to just write it to a separate file and load that file, and you get syntax highlighting in your editor, and you don't have any issues with ES6 support, for example. If you use advanced ES6 features on the Frida side that the local node side doesn't support yet, you won't be able to use those features. Anyway, let's try this with Python. Yeah, okay, and we have to actually replace the address function because it's going to change. So yeah, that's Python. All right. So yeah, as I said, there are several language bindings. There's also a .NET binding for Windows users, and there's a QML one for Qt people. But it's the same thing, just there's subtle variations in method names. Like in Python, it's create_script, and it's in JavaScript, it's create_script in camel case. So anyway, we'll continue with the Node.js binding just to keep it simple. And now we can look at how we can change function arguments to manipulate the behavior of the target application. So let's create a modify.js, paste in this code. So as you can see, it's pretty much the same code, but this time we are actually doing this. So we're this args argument that we get here is like a virtual array, and when you assign to it, there will be a C++ callback called, and it will actually replace that argument at index 0. But it's important to note that Frida doesn't know anything about the number of arguments, so it's up to you to know, or you're supposed to know that. So you might go out of bounds here if you try a very high index. But yeah, here we'll just replace the first argument with a new number, and each argument is represented as a native pointer, and there's a shorthand PTR in Frida for creating those. We have native pointers instead of just using JavaScript numbers because a JavaScript number cannot represent 64-bit pointer values because it's a double. So that's why we have these native pointers, or here we use the shorthand for creating one. So we can try running this, and again we need to replace the address of the function. So now we're going to do this run this modify script, and if you pay attention on the left-hand side now, run it there. Now we're replacing the first argument. So the function is receiving a different argument. And if we detach, you'll see that it goes back to normal. All right. Any questions so far? All right. So yeah, so now we've looked at how you can hook function calls to observe them, how you can play around with change arguments, and you can also actually call functions, arbitrary functions in memory, because Frida has an FFI, libFFI integration for that. So we're going to actually create a call.js, and this time the host side part is pretty much the same, except we don't care about messages coming from the other side. I'm going to go talk a bit more about what messages, how that stuff works later, but just for now know that it's if you call send on the target side, there's going to be a JSON message delivered to the host side, and you can install a callback like we did earlier. And it's also possible to send messages in the other direction and receive them on the target side, like inside the target process. So again, we need to replace the address. So we're just gonna take one of the. There we go. So our script now, in this case, the script we inject and run in the other process, we create a native function. It needs the address of the function in memory. It needs the return type and the types of each the type of each argument. And here it is just one argument, so it's an int. And that's it. Then we have an object that behaves like a JavaScript function, and we can call it like this to actually call that function. And now if we run this, and you pay attention on the left side when I run it now, see that there's 3 function calls in succession happening, and that's it. So yeah, now as I talked about messages, that's how it's a quite low-level primitive, but it allows you to exchange information back and forth. So it all depends on your application. In some applications, you may not want to send any messages at all. Maybe you'll just have this agent or this code that you inject on the other side in the target process just running there autonomously, and there's no need to communicate with it. In other cases, maybe it's an interactive thing, then you'll be going a lot of sending messages back and forth. Or in other cases, maybe you'll just send progress notifications. So it all depends on the application you're building. But I'm just going to demo here how really the basics work. So we have a send.js. Yeah, so when we get the message on the Node.js side, we just console log it so you can see what it looks like. So here on the other side, we do a send, and we give it like a complex, or not complex, but a nested JSON object with some stuff in it. And then we crash, just to show you how that's handled. So we do send. We run this now. If we run this now, you're first going to see the actual JSON object that we sent here, and it's sent as is. The thing is, it's wrapped inside. So the message you get has a type, and it's a send because it was sent by the send call, and the payload contains the JSON object, whatever you gave it. And then when there's an unhandled exception, you get a different type of high-level message here with type error and file name and line number description. And that's how you can debug issues with your scripts. Well, one way to do it. So I should also note that you can access memory. So if we here, for example, try read byte array from this address, and that's quite invalid. You should see access violation reading 0x1. So we do handle attempts to access invalid memory addresses. But yeah, it's not bulletproof. I mean, if you call a function, if you do a native function and call it, and it's at an address that contains garbage, well, it's going to crash the target process for now. There's no parachutes there. So let's see. Yeah, and the same if you want to receive messages going in the other direction. If you want to, it goes like this. Let's just copy it and then I'll explain it. So, so here the script just defines a handle message function, and it calls receive, and that's a single shot thing. So you install like a callback, and this is called on the next message received. So we handle it by just sending a message back with the number we got in multiplied by I, and I is incrementing with every message we handle, and then we call receive again to go receive the next message. And on the other side, we just load the script, and we post two messages with two different numbers, and we run this. So yeah, you'll see that it responds back. So that's how you can receive messages. Yep. Now, in some cases, maybe if you're hooking a function and you need the debugger side or the tool you're building, you need to actually process something there. One silly example could be if you're building a live translation app. There's an API for drawing text, for example, rendering text, and every time you see a new string, you could send it over to the other side and wait for a reply, and the other side could go hit Google Translate and actually translate the text and reply with it. It can actually block on the other side and waiting for a reply for that message, to that message. So show that here. So here we just define on the host side when we get a message, we take the number out of this number parameter. We just post the message back with number multiplied by 2. And then on the other side, yeah, I'm just going to need that. So and replace the function address here. So when this function is called, we're going to send the number of the argument, and we're going to receive, call receive to get the next message from the other side. Receive actually returns an operation that you can call wait on to block, waiting for the reply. This is not something you will have to. It's not something that you'll generally do, but just good to know that it's possible if you're in. PC.js. So run this now. Yeah, you should see now that the numbers are doubled on the other side, like from here. And now if we kill this tool, then it's going to go back to normal. All right. Yeah. So that concludes the basic basic walkthrough of the API. Any questions so far?
On the operation wait, how do you know that that's done? So like, is there a callback there, or is that a promise opt-out wait, and you just do a then on that?
Yeah, so that wait there is actually blocking. So this call here is blocking. Okay. So it lets go of the V8 lock, and it lets other threads run again, and it's just this particular thread is suspended now, waiting for the next message incoming. So so after this callback has been executed, because we got a message from the other side, then this is going to unblock and continue running. So now let's maybe go on iOS, and just because now we've been having some fun on the desktop, but kind of mobile is more interesting, so let's go there. So we have a slightly more involved example here. So let's just run through it. So so here we're, instead of Frida attach, we're doing Frida get USB device. That means, the thing is, when you do Frida attach or Frida spawn and so on, it's using the local system that's represented in the API as a device, but there's like the shorthands at the top level of the API to save you some typing. But you can actually get devices, enumerated devices, like USB devices. We do integrate with USB MuxD that iTunes provides to discover iPhones and iPads or iOS devices when they're attached and detached. And you can actually subscribe to notifications to react when they're plugged in and unplugged and so on. So here we just have a convenience API to get a USB device. If you have multiple, it's not really defined which one you'll get. So this is just a shorthand. You can enumerate them if you want. But anyway, we get the USB device, and we spawn the App Store app. So we're going to do early instrumentation here. We're just not just going to attach. We're actually going to spawn the app, and then we're going to attach to it. Because this spawn call here will actually spawn the app, but the main thread will be suspended before it's able to run any code. And or almost before. It's just gonna sit in a mobile substrate plugin that we use on iOS for this particular thing. And then we're gonna attach. That's just gonna load our agent, like a library inside that remote process. And we're gonna create a script, and we have a script here just like before, inline. That's JavaScript. We serialize, and then we're gonna any message we get, we're just gonna, if we get a ready message, we're gonna resume. That means that the main thread will start executing or continue executing. So that means we have instrumented the APIs we're interested in, so we don't miss any when they're called early. Any other message, we just print it. So we load the script. So now on the other side, we've just spawned the process, and we are executing the script. So we enumerate the exports of the libcommon crypto library, and there's both functions and variables of data exported. So any function we actually attach to it with the interceptor, like you saw before, and we just send an event whenever it's called with the name of the function that was called. And then in case interceptor isn't able to attach to the function, which happens with really short functions, like less than 4 instructions, so we're just going to ignore them and skip. And when we've enumerated and actually instrumented all the functions, we're going to send a notification to the host side that will do this, device resume, to let it start executing. So yeah, I have a device here now. I'm going to run it, and yeah, I can actually close this other tab. So here you saw a lot of functions getting called early in this app. But, well, actually this is such a common task that maybe there should be an app for that, and there is. So you can just install the Frida Python package, and you can use the Frida trace tool. And you tell U for USB, and I want to actually spawn an app. If it starts with / like here, it's going to be like it's actually going to spawn a process with that program on the file system. But if it doesn't start with a / like here, it's an app ID, and then it's launched a bit differently. And here we're telling it just include everything in libcommon crypto, like all the exports, instrument all of them, and you can run this. And there we go. So maybe it's the demo effect. Let's see. Let's try again. Able to communicate with loader. Yeah, okay, here we go. So now we're instrumenting the App Store app from the beginning, and this tool doesn't know much about the actual functions getting instrumented. But what it does know is it uses the thread information, because this onEnter here has like this thread ID, for example, that has the thread ID, and you can use that to, like here we color the threads differently based on the thread ID, and there was a printer header, so you see that calls are happening in different threads. And there's also depth that you can look at to see the call stack depth, and that's how we do the indentation here. So you'll see recursion happening, like encode calls these functions. So there's also some other things like this context, where you can look at the registers like PC and SP and so on. Yeah. So that's Frida Trace. On Mac and Linux or Unix, it actually tries to do look in man pages, so it can show you, so it knows how many arguments and can show you the arguments, but that's quite limited. The thing is, this tool generates a directory on the file system called __handlers ___ with each library here, and one file per function that's instrumented. So yeah, let's show that. It's a bit buggy today. So now if we look here, for example, at CNN encode, there's a JavaScript file generated on disk by this tool, and the tool will actually look at, it will actually detect file system changes. So we could now update this, and if we play with, yeah, here you see the change I made. So you can iteratively improve these hooks that you write, and as you gain a better understanding of the API, or as you look at man pages and so forth. But yeah, and it's generated with a boilerplate explaining the API, but you can of course strip that out. That's essential. The essence of this. So anyway, let's move along. Yeah, let's just show that you can actually interact with Objective-C APIs as well on Darwin or Mac and iOS. So here, gonna get the USB device like in the other example, but instead of spawning an application, we're just gonna get the frontmost one, and we're gonna attach to it. And the script here actually uses Frida's Objective-C integration, so it schedules a function here on the main thread where we're gonna interact with the UI, and we get the key window, and then we call the recursive description of, which is an Objective-C function, and that gives us a string, and then we do, or NS string, and we do toString to get a JavaScript string, and we just send that over. So if I now have, let's see, .ui. Here you see the UI dumped. Right. Any questions so far? You can all still hear me?
Yeah, we can hear you. Sorry. No questions, I guess.
Cool. So, yeah, let's move along. You can also show the Android counterpart to that, where we support. We have an integration with Dalvik. There's no support for art yet, but that's planned. In this case, instead of get USB device, we'll do get remote device. That's actually that actually does is connects on localhost port on a specific port, and you are supposed to forward that port to a device, like in this case ADB forward, or you could use an SSH tunnel to connect to a remote device, and then we attach to an app we have made specially for this purpose, just to demonstrate this. And whatever messages we get, we print them and we load the script. And then when the script is executed, it will perform something in the Dalvik VM. So we attach to the VM, and that's what happens when you do Dalvik perform. So this function here is run while attached to the VM. We're just gonna get a class from the application, and we're gonna hook one of the Java functions methods. Sorry, that there's a main activity has an is registered implementation that returns a boolean, and we're just gonna log and return true. The default this test app that we're gonna show returns false there, so it reflects in the UI. To prove, and I keep forgetting the syntax. So forward the port. We need to ADB to actually run the Frida server on the device. Okay, that's running. So now we can do like Frida PS. That's another console tool installed by the Python package. We can use R for remote, and gives us a list of processes with the PID and the name each. So now if we open the emulator here, we run our Hello World app, we should see it here in the list. I think, yeah, there it is. RE Frida Hello World, PID 2155. Yeah, I didn't actually save that file, did I? No. So first, let's just hit the sign in button, and nope, not registered. And yeah, that's what happens. I actually use the script. And it should now be ready. So now this function should be hooked. So if we hit this button again, our replaced implementation should be called instead of the app's implementation, and they're welcome. So we have now modified the behavior of this Android app by just hooking one of its Java methods. All right. Yeah, any questions so far, by the way? All right. So another use case that might be interesting is injecting errors into an application, like to answer the question of what would happen if it's unable to connect to a certain port, or different scenarios. And here I have a slightly larger example showing that how you can do that. Gonna shut down a few things here. So this example here is a bit more complicated. We'll spawn like locally the program that you provide the path to, and any arguments you give it. We attach, and then we create a script, and the script will actually instrument both connect and connect $no cancel. And it will actually use a different API of the interceptor this time. Instead of attaching to a function to get like a callback before and after, or enter and leave, we will replace its entire implementation. That means we need to actually know about the argument list, the types, and so on. So here we replace the connect implementation with our own implementation by having a native callback. That's kind of the counterpart to a native function that we saw earlier. This is for receiving callbacks from native code. So instead of calling functions, you can actually give a JavaScript function as a callback to native code. In this case, we just replaced the implementation of connect with our implementation in JavaScript here. And the signature, it receives an int and accepts 3 arguments, int, pointer, and int. So the second argument is the address, the sock adder. So we add 1 to that pointer, and we read an untimed 8-bit integer from that address. And that's a family, and we check if it's AF INET or AF INET 6. If so, we go into the sock adder IN or IN6 and read out the ports. And depending on the family, we read out the IP address. And for the sake of this example, we just check if the port is one of these 3 ports. We instead of calling the original implementation, which we have up here, connect, we just set erno to econ refused, which is 61 on Mac, iOS, and return -1. Otherwise, we chain up to or call the actual implementation of connect. And any other families like Unix socket and so on, we just forward. We don't do anything. And then we call it send ready when we have finished instrumenting this API, so that the other side can call resume and actually start executing the main thread of the application. So if we now run this, and Spotify, for example. Oh yeah, I missed something here. I think there should be a use strict at the beginning. Okay. Slight error in the example. So yeah, connect. Yeah, friend feed is not available offline. Yeah, the UI is reflecting that there's no connectivity, and you can see here it's trying and it's getting blocked when it's trying. And there it gave up and concluded there's no internet connection. So if I now run this app directly without this instrumentation, it will be quite different. And just it will work. Okay, so that's about injecting errors. Now let's go really deep here. So something that's quite interesting, maybe especially for fuzzing and also reverse engineering in general, is when you're receiving something from the network, you would like to know like the execution path when the receive returns, and how often the data that was read is processed, and then the next receive call happens in the typical main loop application. But very often that's the case, and you would like to see like a log of all the instructions that is executed, or all the calls, for example, so that you can correlate the data that you received with the execution path taken. And you can then change the data, and you can see how it changes the execution path, basically. So here I have a slightly larger example. A lot of this is there because the API sucks a bit at the moment with this part of the Frida API is called a stalker, and it's about tracing code. And it works through dynamic recompilation, so it's recompiling the code as it's executing, but it's doing that on a per thread basis, so you can make it follow just one thread. And yeah, I'll go into detail when we look at the code here. So yeah, trace. So yeah, we attach to the PID you give it, and yeah, the script is here. I'm going to go into that, and we receive some different messages, like for feedback. Plus ready means well, we print console that the applications. We're waiting for the application to call receive because we have instrumented the API, and result. When we get the final result, then we detach the session that we attached, attached here. And the script here is a bit more interesting. So these functions receive and receive all or no cancel. Each of them we attach some callbacks so that on leave, and we have a state. It's a state machine here. We're in the waiting state initially. We start out in the waiting state, so if we're in the waiting state, yep, that's where we are in the beginning. So we set the state to stalking, and we take note of the thread ID, and then we stalk or follow ourselves, basically. We can also give it a thread ID here, but in this case, we want to stalk ourselves, so we just met that argument. And we say we're interested in call events. That means anytime there's a call instruction, there will be an event produced. And we also give it a callback on receive that's given a batch of events. And this is called periodically. And you can configure how often you like it to be called and so on. And we just accumulate the blobs of events that are produced. And yeah, so we start here following, and then so here we return from the receive. And then on the next receive in on enter, the state will now be stalking because we set it here. And this thread is actually the stalk thread ID. If it's another thread, we ignore it. We change state to collecting. And then we unfollow this thread. And now, when we get events, we check if we're in a collecting state, and we send off the results and go to the done state. So yeah, we instrumented this API now, so we send the plus ready. This is in the beginning, and when we send the results, actually, this is the sucky part of this API. You get like a blob of binary data, and you need to poke into it and look at the C header file to know the structure of the events, and it really sucks. But this API needs to be improved, so because you need to find a good trade-off with performance and usability there. So there's also another one on call summary. You can install a callback, a different callback here, and you get like a key value mapping of the address called and the number of calls. So that's more efficient if you're just interested in like which functions exist in this binary and how often are they called. So yeah, the rest here is just event parsing, so it's not really interesting. We could try this. And we could attach to Spotify, for example, because it has some socket code for sure. So yeah, now we're waiting for the application to call receive. So let's just do something in the application. So it will hopefully do receive. Maybe, yeah, there we go. Boom. And now you see the results are sent over and they're printed on the Node.js side. Yeah, I think there was a lot of calls happening here. Yeah. anything there. Okay. And here's the events, and so you have the address that have the call instruction, and you have the target of the call, and you also have the depth, the call depth, so you can see function calling a function, calling a function, and so on. And now you could build a more advanced app that would save or sample these and compare them or diff them based on the data that's input and so on. All right. So, any questions?
Yeah, I had one going back to the Android support. Kind of curious about like at what level is the Frida stuff working, and is it simple, just like you've hooked the Dalvik here? Is it pretty simple to hook into the native libraries or anything that the apps use?
Yeah, definitely. It's exactly the same API as earlier. I'll show you. So typically you would use process. And you could do no, actually, the easiest is module. Module find export by name. So you could say libc.so as the module, and you could say any function you would like, or you could do process enumerate modules, which will give you a callback on each module and it finds, and then you can do things based on the modules, like OpenSSL. You recognize OpenSSL, and you then go on to enumerate the exports of OpenSSL, like here, and then you could attach to the functions there, for example. And Dalvik, you can also enumerate loaded classes if you're curious about what the app has loaded.
As far as installation goes, you're not replacing or building this into any of the system. It's just a standalone binary?
Yeah, that's correct. So it's just a binary you have to run as root, and that's it. That binary is listening on a port, and then you forward that port, and you do the rest from the host, basically.
All right. So basically, if whatever process you're debugging, Frida's in that one, but it's not touching any other process that's out there. The rest of the operating system is untouched.
Yeah, that's correct. You have to explicitly attach or spawn a process. It will, there's no mobile substrate kind of mode where it's attaching to everything. It's just you have to do it, yourself explicitly.
So one of the cool things I thought I wanted to run by you. So if we wanted to detect static calls to OpenSSL within an app, you have some functionality there to scan memory, right? So would we be able to build a signature for some of the static calls, perhaps, and instrument them? Do you see that as realistic?
For simple cases, I think that's good. But if we want to build like a system, maybe it's better to combine that with Radar and use that to generate the signatures, and then with these signatures, once you figure out the addresses, then you'll attach to those functions. But it all depends. That's something we should look more into, like what's the best approach there, because if this memory scanning is quite simple, so I can show you it here. And you just give it a pattern like this, the hex bytes and question marks if for any value of a certain byte. But that's it. It's very limited. So for more advanced matching, I think combining this with Radar would be really cool.
Or even Yara, perhaps.
Yeah, I think that's where we need to combine static analysis with dynamic analysis that this does, basically.
Yeah, that's definitely pretty exciting.
Let's see. Yep. Yeah, there's no Francisco. There's no support for to answer your question if it's possible to graph the path execution. There's no graphing in Frida, so you'd have to combine it with other tools to do that.